We then further consolidate the two resistors, T and R_EQ, into one resistor. We will call it R_total. Using series resistor rule, R_total equals T plus R_EQ equals 10 ohms plus 5 ohms equals 15 ohms. The consolidated 1 voltage source, 1 resistor circuit is shown in Figure 1.13. Figure 1.13, simplified 1 voltage, 1 resistor circuit. We now can simply use Ohm's law to calculate I_total. I_total equals 5V/15 ohms equals 0.33A. At this point, we can apply KVL to make sure the analysis is valid. 5V plus 0.33AX 15 ohms equals 0V. To figure out I_A, I_B, we first calculate the voltage drop across T using Ohm's law. Voltage drop across T equals I_total x T equals 0.33AX 10 ohms equals 3.33V. Since voltage at left side of T is 5V and the voltage drop across T is 3.33V, the voltage at the right-hand side of T, node A and B, is voltage drop across T equals voltage at left side of T, voltage at right side of T, 5V, voltage at the right side of T, equals 3.33V, voltage at the right side of T, equals 5V, 3.33V equals 1.67V. It's crucial to recognize that voltage across a device means the difference, subtraction, between two nodes. Now we can use Ohm's law again to calculate I_A and I_B. Because voltage at right side of T is common to node A and B, voltage at node A equals voltage at node B. I_A equals voltage at node A equals 1.67V/10 ohms equals 0.167A. I_B equals voltage at node B equals 1.67V/10 ohms equals 0.167A. To prove the analysis is correct, simply use KCL, which states that I_total equals I_A plus I_B. I_A plus I_B equals 0.167A plus 0.167A equals 0.33A equals I_total. It checks out. Current divider rule. The current divider rule states that the current on one branch is the total current multiplied by the ratio of total current. When seeking current A, the numerator contains resistor B and vice versa. Using Figure 1.12 in the previous example, I_A and I_B can be easily calculated. Notice if both resistor sizes are the same on each branch, the current amount will be equally divided in a parallel circuit. If the resistors A and B are different sizes, the current is less on the branch that has the larger resistor and vice versa. This concept is illustrated in Figure 1.14. In this example, I_total equals 2A, A equals 20 ohms, B equals 10 ohms. This shows that I_A is less than I_B, A's resistance, B's resistance. To further prove this is correct, apply KCL. I_total equals I_A plus I_B equals 0.66A plus 1.33A equals 2A. It checks out. Figure 1.14, resistor size versus current amount. Voltage divider. The voltage divider is used all too often. We will start with the definition, then use simple circuits to explain it. Just like it sounds, a voltage divider divides voltage. The word divides does not mean there is a mathematical division, it means the voltage is reduced by the resistors. Below is a simple series circuit, see Figure 1.15, to explain voltage divider. Figure 1.15, simple series resistor circuit. The explanation of this circuit is simple, not surprisingly, using Ohm's law. There is only one current branch in this series circuit. The current can be calculated using Ohm's law and the series resistor rule. The voltage at node A is 10V, connected to a 10V voltage source. The voltage across IR drop resistor A is the potential difference between node A and B, i.e., voltage at node A, voltage at node B, or it can be calculated using Ohm's law, 0.5 AX 10 omega equals 5V. Once again, it's important to realize that voltage drop across a resistor is the potential difference between two nodes. Knowing that voltage at node A is 10V, and voltage drop across resistor A is 5V, voltage at node B can be found using voltage definition. Voltage drop across A equals voltage at node A, voltage at node B, 5V equals 10V, voltage at node B. Voltage at node B equals 10V the 5V equals 5V for voltage drop across resistor B. It would be voltage at node B, ground, 0V equals 5 to 0 equals 5V. All voltage drops, IR drops, are shown in Figure 1.16. Figure 1.16, voltages across A and B. There are voltage drops across each resistor. Voltage was reduced, divided, from the 10V voltage source. In other words, voltages across each resistor cannot exceed the 10V voltage source. Some use this formula when it comes to voltage divider. RA is in the numerator when calculating VA, RB is in the numerator when calculating VB. VA and VB are simply the ratio of individual resistance, RA, RB, over the sum of all resistances, RA plus RB, in the circuit. If you look closely, the VA-VB formula comes from Ohm's law and series circuit rule. We know that the current going through A and B are the same, series circuit rule. VA/10 ohms equals VB/10 ohms. This current can be calculated from the 10V source in series with RA plus RB, Ohm's law.